Distributed denial of service protection and availability planning are both about the same outcome: keeping critical services functioning when the environment is stressed, whether that stress comes from accidents, failures, or hostile load.
In practice, adversaries do not need to compromise your systems to cause meaningful damage if they can make customers unable to reach you or employees unable to use essential tools.
Availability is also a trust issue because repeated outages erode confidence and can turn a technical event into a business crisis quickly.
The challenge is that availability under attack is not solved by one product or one control because it depends on capacity, architecture, detection, and response discipline working together. When you treat availability as a first-class security objective, you design networks and services so they fail gracefully, recover quickly, and remain observable even when traffic is hostile.
Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A distributed denial of service event is essentially a resource consumption problem where floods consume bandwidth, connection state, or application resources until legitimate traffic cannot be served. Bandwidth exhaustion targets the links that connect your services to the outside world, saturating them so packets cannot enter or leave at acceptable rates. Connection state exhaustion targets devices and servers that must track sessions, such as firewalls, load balancers, and web servers, forcing them to spend memory and processing on attacker-driven connections. Application resource exhaustion targets the expensive logic above the network layer, pushing application threads, caches, and databases into overload through requests that are syntactically valid but operationally costly. These are different failure modes that require different mitigations, which is why you start by being precise about what is being exhausted. If you assume every distributed denial of service is just bandwidth, you will miss the more subtle attacks that bypass brute force defenses. Volumetric attacks are the most visible form because they overwhelm links with very high traffic rates, and their intent is to fill pipes rather than to exploit nuance. When the ingress or egress capacity of your upstream link is saturated, the service becomes unreachable regardless of how healthy your servers are, because packets simply cannot be delivered reliably. Volumetric floods may use large amounts of traffic from many sources, often leveraging compromised devices or amplification techniques, and they are effective because the Internet is built to forward traffic, not to verify intent. Your own perimeter devices may not even see the full attack if the upstream link is already saturated, which is why mitigation often has to occur before the traffic reaches your network. The defensible approach is to assume that any Internet-facing service can be targeted with traffic volumes that exceed local link capacity, then design accordingly. This pushes you toward upstream mitigation, distributed architectures, and careful capacity planning. Protocol attacks exploit weaknesses in state handling and network stacks, often using traffic that is not necessarily large in bandwidth, but is costly in terms of tracking and processing. These attacks target how devices allocate resources for half-open connections, how they handle unusual packet sequences, and how they manage tables that track session state. A firewall, load balancer, or server can be forced to spend disproportionate effort on connection attempts that never complete, or on packets crafted to trigger expensive processing paths. Because the volume may be modest compared to volumetric floods, these attacks can slip past defenses that focus solely on megabits per second and instead succeed by exhausting concurrent connection capacity or processing cycles. Defending against protocol attacks often involves tuning stack behavior, using state-aware protections that can drop suspicious patterns early, and pushing mitigation to devices and services designed to withstand high connection churn. The key is recognizing that small traffic can still be devastating if it targets a resource that is scarce. Application attacks are often the most frustrating because they target expensive operations like search, login, or database queries, and they can look like normal user behavior at first glance.
An attacker may repeatedly request pages that trigger heavy database activity, or they may exploit login workflows that involve password hashing, multi-step validation, or external calls, forcing the service to spend meaningful compute per request.
Unlike simple floods, application attacks can be carefully shaped to avoid obvious rate thresholds and to blend into baseline traffic patterns, which makes detection and filtering harder. The defensive posture relies on understanding which endpoints are expensive, controlling those endpoints with rate limits and challenges, caching where appropriate, and isolating back-end resources so one hot path does not collapse the entire service. It also depends on robust observability, because you need to see error rates, latency increases, and saturation indicators quickly. Application layer resilience is as much about engineering and performance discipline as it is about security appliances. Mitigation strategies combine scrubbing, rate limiting, filtering, and traffic engineering, and the mix you choose should map to the attack type and to where you can most effectively apply control. Scrubbing refers to sending traffic through specialized infrastructure that can absorb high volumes and filter malicious patterns before forwarding clean traffic to your origin. Rate limiting restricts how many requests or connections a client or pattern can generate, which is useful for both protocol and application attacks, but must be tuned carefully to avoid blocking legitimate surges. Filtering blocks known bad traffic signatures, suspicious geographies when justified, malformed packets, or traffic that violates protocol expectations, reducing wasted processing. Traffic engineering includes routing decisions, upstream controls, and architectural patterns that influence how traffic reaches you, allowing you to steer load away from constrained links or toward mitigation centers. The common theme is that mitigation is layered because no single mechanism reliably stops every form of distributed denial of service without unacceptable collateral damage. Anycast routing is a powerful technique because it distributes traffic across locations to absorb spikes, reducing the likelihood that one site becomes the single point of failure. With Anycast, the same Internet Protocol address is advertised from multiple geographically distributed locations, and the Internet's routing system delivers clients to the nearest or best path location based on routing decisions. In a distributed denial of service context, this means attack traffic is spread across multiple points rather than concentrated on a single data center link, which improves absorption and buys time for filtering and mitigation. It also improves latency for legitimate users because they are served by closer points, which can help maintain usability during stress. Anycast does require careful planning because routing changes can shift traffic patterns dynamically, and you must ensure that each site can handle the portion of load it attracts. When deployed well, Anycast turns a single exposed endpoint into a distributed service surface that is harder to overwhelm. Content delivery networks and edge services further reduce origin exposure and spread impact by moving caching, filtering, and request handling away from the origin and into distributed infrastructure. When static content is served at the edge, requests never need to reach the origin, which reduces back-end load and reduces the attack surface available for origin exhaustion. Edge-based filtering, web application firewall behavior, and bot management can stop malicious traffic before it triggers expensive origin processing, which is critical for application layer attacks. The edge also provides a place to apply rate limits and challenges at scale, often closer to the source of traffic, which reduces the amount of hostile volume that reaches your core. The architectural point is that your origin should be shielded and treated as a protected resource, not as the first line of defense on the open internet. When you combine edge services with strict origin access controls, you force attackers to fight distributed defenses rather than probing the back end directly. Capacity planning is the unglamorous backbone of resilience because it anticipates peak load and mitigates resource exhaustion conditions that can occur even without an attack. You start by understanding normal peak traffic, growth trends, and burst characteristics. Then you plan headroom so legitimate surges do not push systems into failure modes that look like attacks. Capacity planning also includes evaluating connection limits, thread pools, queue depths, and rate limits so that under stress the system degrades predictably rather than collapsing unpredictably. In distributed denial-of-service events, headroom matters because it determines how long you can sustain service before mitigation fully engages, and it determines how much collateral damage you can avoid while filtering. If you run systems near saturation in normal times, you have no buffer when conditions change, and even modest attacks can cause outages. Resilience requires honest accounting of limits and disciplined investment in capacity where it provides real risk reduction. Redundant links and providers reduce dependence on one transit path, which is one of the most direct architectural defenses against link-level saturation and upstream failures. If you rely on a single internet service provider or a single physical path, then an attack or outage that affects that path can cut off service even if your internal systems are healthy. Multiple links, diverse physical routes, and multiple providers create options for rerouting traffic, balancing load, and maintaining connectivity when one path becomes degraded or saturated. Redundancy also supports mitigation because you can steer traffic toward providers with better scrubbing capabilities or toward paths that are less congested during an event. The security benefit is not only in survivability but also in leverage because multiple providers allow you to coordinate mitigation with upstream partners more effectively. The practical requirement is to ensure redundancy is real, meaning paths are truly diverse and failover behavior is tested rather than assumed. Health checks and failover mechanisms shift traffic when endpoints become unhealthy, turning localized failures into manageable events instead of systemic outages.
Health checks continuously evaluate whether a service instance, a load balancer target, or an entire site is functioning, often using application-aware signals rather than simple connectivity. When health checks detect failure, failover mechanisms can remove unhealthy endpoints from rotation and direct traffic to healthy ones, preserving availability even as components fail. In high-availability networks, failover can operate at multiple layers, including server pools, load balancers, and site-level routing, and the design must ensure that failover does not create loops or oscillations under stress. Failover is especially important during distributed denial-of-service events because parts of the system may become overloaded or degraded, and the ability to shed load or reroute can prevent cascading failures.
The goal is graceful degradation, where the system continues to serve what it can while maintaining control and recoverability. Monitoring during stress is what keeps you from flying blind, because you need to watch latency, error rates, and saturation indicators to know whether mitigations are working and where the bottleneck has moved.
Latency increases can indicate congestion, overloaded application layers, or upstream routing changes, and they often show up before complete outages.
Error rates reveal whether the service is failing to process requests, which is critical for distinguishing between traffic reaching the edge and traffic being successfully handled by the origin.
Saturation indicators include link utilization, connection table usage, queue depths, and server resource consumption, and these tell you which resource is being exhausted. During a live event, conditions can shift quickly as attackers change tactics or as mitigations reroute traffic, so continuous monitoring is necessary to keep response aligned with reality.
The objective is not to collect every metric, but to maintain a clear view of service health and constraint points as the event evolves. Incident coordination is the human layer that turns technical controls into a coherent response, including communications, escalation, and post-event analysis artifacts.
Communication is essential because stakeholders need accurate updates about impact, mitigation status, and expected service behavior, and those updates must be consistent to avoid confusion and reputational harm. Escalation ensures the right teams and external partners are engaged quickly, such as internet service providers, mitigation vendors, application owners, and leadership, because distributed denial of service response often crosses organizational boundaries.
Post-event analysis artifacts include timelines, traffic characteristics, mitigation actions taken, and lessons learned, and these artifacts matter because they improve future resilience and support accountability.
A disciplined post-event analysis also helps differentiate what worked from what merely appeared to work, which is crucial for improving defenses over time. Without coordination, even good technical controls can be applied inconsistently, too late, or without the governance needed to sustain them.
Distributed denial of service resilience combines mitigation services with robust network design because availability under attack is both a traffic problem and an architecture problem. Floods can consume bandwidth, connection state, or application resources, and each category requires targeted defenses that match how the resource is being exhausted. Scrubbing, rate limiting, filtering, and traffic engineering form the core mitigation toolkit, while anycast routing and edge services distribute load and reduce origin exposure. Capacity planning provides the buffer that prevents routine peaks from becoming outages, and redundant providers and links reduce dependence on any single transit path. Health checks and failover mechanisms keep service available as components degrade, and monitoring ensures you can see latency, errors, and saturation as conditions shift. Incident coordination provides the operational discipline to communicate, escalate, and learn, turning one event into improved readiness rather than repeated surprises. When these elements are designed and practiced together, availability becomes a defended property rather than a hopeful assumption. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.